Hello everybody, I'm Dr. Ayman Noor. I'm Assistant Professor at the Electrical and Electronic Engineering Department of the University of Omar al-Mukhtar. I'm here to present to you our work titled Partitioning Streetlights Load on a Grid Photovoltaic System as an Alternative Solution for Illuminating Al City Roads. This work is realized by me and the cooperation of my co-author Dr. Mohammed Khattab. As outlined, my presentation firstly starts by highlighting the solar potentiality of selected site. Secondly, the determination of a problem will be done. The suggested solution and goals of the study will be identified. Thirdly, the studied system will be detailed and explained. Before concluding, the obtained results will be exposed and commented. To highlight the potential of solar resources of selected region, a trial version of Omar Pro software is used because it has the ability to upload the resources of a certain site if it is connected to the internet. So the city of Al Baida, that's located at the east north of Libya, is selected in order to extract its solar potentiality. Then a hybrid system simulating the concept of our study and consisting of PV panels, grid, storage batteries, bidirectional converter, and a constant load is built as shown in the schematic diagram here. The utility grid is connected to a C-bus bar, while the PV panels, a string of two storage batteries, and the LED lamps or lighting load are connected to the DC bus bar. A converter is interfaced the two bus bars. Finally, the daily profile of lighting load is introduced. It has a constant value as shown in this figure. When the running of simulation is completed, we can showing the results. For example, here we have the yearly load profile. It is clear that the load consumes electricity during night time between 6 p.m. and 6 a.m. represented by the red color, while it is off during daytime between 6 a.m. and 6 p.m. approximately represented by the black color. The energy production per source is shown in the second figure here. It can be observed that the grid covers the needs of lighting lamps with a constant manner, while the energy generated by the PV panels is dependent on the seasonal radiation. According to the Homer Pro report, the percentage of participation due to the grid is about 17.1%, while it is about 82.9% for the PV panels. The power electronics converter operates in two modes: an inverter mode converting the DC generated power by the PV panels to AC power and returns it to the grid during the daytime period. The second mode is the rectification mode, converting the AC power available on the grid into DC power during night time to charge the batteries and to cover the needs of lighting load. Other results concerning the purchases and sold energies is shown in this slide. Between 6 p.m. and 6 a.m. the system purchases an amount of energy from the grid represented by the orange color, while it sells the generated energy by the PV panel to the grid during daytime and depending on the seasonal radiation. This slide focuses on the problem of standalone PV systems. These systems operate individually without the connection to the grid. They are consisting of PV panels, storage batteries, and charger controllers, and usually used to feed a small applications as shown in this diagram. These systems suffer from problems like battery autonomy, low efficiency, and the high cost. In a previous publication, presented in the IREC 2019. We studied this kind of system for street lighting application and we obtained this result appearing here. This result reveals that the battery's charging time is large and the gain in state of a charge is small. In addition, when we repeated this simulation starting from the last level of shock of about 50%, we found the same result but with an excessive discharge and that affect the lifespan of storage batteries. To solve this problem, the increasing of the number of PV panels per lighting pole may be considered as a solution, but this is not applicable because that will increase the cost and stressing the lighting poles. So, as an applicable solution, we are with the adoption of a grid-connected solar PV panel system shown in this diagram. The system contains two sources that alternate to supply the storage batteries and the lighting load. At this stage, we consider only that the converter interfaced the grid and the rest of system operates as a rectifier, that is mean an unidirectional converter. Overcoming the disadvantages of standalone PV systems becomes the objectives of our study. We expect a rapid charging period and high shock gain. Also, an acceptable depth of discharge will be controlled. In addition, the system will be fixed the number of PV panels at one or two panels per lighting pole. Finally, this kind of system is considered as a rational energy consumption way. In this slide, we give the overall model of the studied system. It built with the help of MATLAB Simulink software. It consists of 6 parts. This one is a one-diode equivalent circuit representing the PV panels model. It has the objective of converting the sun radiation into electricity. The second part has the objective of regulating and raising the outputs of PV panels using DC boost converter. The energy obtained at the boost converter terminals will be stored in the third part called storage batteries. The fourth part models the utility grid. It composes of AC source connected to a step-down transformer. The interfaced converter between a grid and batteries and or load is shown in this 5 parts. A bridge full wave control rectifier is used. Finally, the 6th part represents the lighting load. To performing the simulation, some assumptions are made. We consider that just one pole lighting unit will be modeled. We assume an irradiance profile like this one. It starts with low values as the sun rises, then reaching its peak at the midday and gradually decreases as the sun sets. Finally, it has no value during the darkness. Also, the connection to the utility grid will take place in accordance to a typical load curve as shown in this figure to avoid its peak demand. We suppose that the peak of demand occurs after 10 hours 30 p.m. and just for a short period enough to charging the batteries. Nowadays, this peak of demand may be shifted 2 or 3 hours because the pandemic of COVID-19 that forces the people staying at home. In addition, we assume that the daylight hours are 11 hours. Finally, we realize for simulation through 24 hours with the sequence shown in this table. The first simulation is related to the circuit, including the PV model, boost converter, and the batteries. It takes more than 3 days and presents the daytime starting from 6:30 a.m. until 5:30 p.m. During this simulation, the grid and LED lamps are switched off. The solar energy converted by the PV panels into electricity will be stored in the batteries. The state of charge starts from initial value of 80% and gradually increases until more than 95% as shown in this figure. When the first simulation is finished, the second simulation will be launched. During it, PV and boost converter is switched off with maintaining the grid out of the simulation. The simulation takes more than 1 day and corresponds to the period from 6 p.m. to 11 p.m. The batteries discharge to supply the LED lamps, and the sock decreases from its stocked value and reaches the level of 70% as shown in this figure. When the state of charge level becomes 70% approximately, the third simulation begins from this instant and continues until the batteries become fully charged. During this simulation, the grid supplies simultaneously the batteries and the lamps. The socket starts growing again from its previous value to reach the fully charging as shown here. During this simulation, the PV models and the boost converter are switched off. The last simulation takes more than 6 hours, starting from 1:30 a.m. and continues to 5:40 a.m. During this simulation, only the batteries again will supply the lighting load. The state of charge will decaying from its fully charging value and reaches the level of 80% as shown in this figure. During this simulation, the PV panels, boost converter, and the grid are switched off. I've now come to the end of my presentation. We can conclude that the paper proposed a grid-connected PV system to overcome the problems of a standalone PV system for street lighting application. Using the software Homer Pro, helping us to obtain some results that clearly reflected the high solar potentiality of Al-Baida city. The period of charging due to the PV source is equal to 4.4 times the charging period ensured by the utility grid. The state of charge gain due to the grid is more than 1.5 times of that ensured by the PV system. If we compare our system to a traditional street lighting system where the coupling to the grid continues for more than 10 hours average, a saving of energy with more than 70% is realized. Thank you for your listening.